Welcome to class. In today's video, we'll look at trigonometric expansions using the Moivre's theorem. What we mean here is we will consider power multiples of the cosine function as well as the sine function using the polar representation of complex numbers. Of course, we will do all of this within the unit dx, which means the radius will be 1. As always, please make sure to like, share, and subscribe, and turn on your notification to ensure you do not miss any of our videos. So, let's begin. Of course, when we say we are in the unit x, we simply mean that in this regard, the radius or the modulus is equal to 1. Now, if this is the case, then it means that the polar form of the complex number reduces to z being equal to cosθ plus I sin theta, where theta of course remains the argument. In this regard, we can take the reciprocal of the complex function as 1 divided by cosθ plus I sin theta, such that if we were to take the reciprocal of this function by rationalizing it, we would have that we would be multiplying by cos theta minus I sin theta, and then the denominator would become a difference of two squares, exposing you to cos squared theta minus I squared sin squared theta. Do not forget that I squared equals minus 1, so this would reduce to cos theta minus I sin theta divided by cos squared theta plus sin squared theta, because I squared is minus 1. Now remember that by basic trigonometric identities, cos squared theta plus sin squared theta gives us 1. So this would simply reduce to cos theta minus I sin theta. So it means that if we say 1 over z, which is of course the same thing as z raised to the power of minus 1, we'll have that to be cos theta minus I sin theta. In that same vein, we can talk about the nth power of z raised to the power n. By the Moivre's theorem, we know that z raised to the power of n, of course still in the unit dx, will be cos n theta plus I sin n theta, such that by this reciprocal that we have just carried out, we would have that z raised to the power of minus n, which is the same thing as 1 divided by z raised to the power n, would of course be equal to cos n theta minus I sin n theta as well. Now we have these representations ready. Now what happens when we add some of these representations together? For instance, if we have z and then we add it to 1 over z, what happens? This means we have taken cos theta plus I sin theta, and then we have added it to cos theta minus I sin theta. The result for this is to see that we would have the result to be 2 cos theta. So z plus 1 over z gives us 2 cos theta. Similarly, we would see that from here, we can write that cos theta is in fact equal to 1 over 2 into z plus 1 over z, such that if we take the nth power of both sides, we would simply have in this regard that cos theta raised to the power of n will be equal to 1 over 2 raised to the power of n, z plus 1 over z raised to the power of n. Of course, this would immediately mean that cos of n theta, note that this is different from cos n theta written here. They are not the same thing. This would be 1 divided by 2 raised to the power of n, z plus 1 over z raised to the power of n. This becomes a good representation for the cosine function that we have here. Now, using this same process, we can generate the same thing on the sine axis. This time around, if we take z minus 1 over z, then we would have cos theta plus I sin theta minus cos theta minus I sin theta, such that simplifying this, we would have that the cosine will cancel and we'll be left with 2I sin theta. If this is the case, of course, for z minus 1 over z, it would immediately mean that sin theta will simply be 1 over 2i z minus 1 over z, such that if we take the nth power of both sides, we have that sine theta all raised to the power of n, the 1 divided by 2i raised to the power of n, z minus 1 over z raised to the power of n, which of course is the same as saying sine raised to the power of n theta is equal to 1 divided by 2i raised to the power of n, z minus 1 over z raised to the power of n. Again, this should not be mistaken for sine n theta that we have here. So this gives us a very interesting and significant way of writing these representations. Now, it is very interesting to note that based off this, we can now extend this concept that we have into finding out what the representation for cos n theta and sin n theta will also be. Now remember, we have checked that cos raised to the power n theta will be equal to 1 divided by 2n raised to the power into z plus 1 over z into the power of n. And then sin raised to the power of n theta is equal to 1 over 2i all raised to the power of n into z minus 1 over z raised to the power of n. However, in the case of cos n theta, what happens in that regard? Well, it's simple to note. Since z raised to the power of n equals cos n theta plus I sin n theta, and we know that by the Moivre's theorem, this is the same thing as saying cos theta plus I sin theta all raised to the power of n, of course, because z raised to the power n is just expressible as cos theta plus I sin theta all raised to the power of n. Then, in this regard, it would mean that cos n theta simply represented just the real part of this expansion. Therefore, we can say that cos n theta, which is of course the real part of z raised to the power n, will simply just be the real of cos theta plus I sin theta raised to the power of n. Which means if we expand this binomially, the real part of whatever we have must be equal to cos n theta. And then the imaginary part of what we have must be equal to sin n theta. So we have imaginary cos theta plus I sin n theta plus I sin theta raised to the power of n. These are very important concepts that we have put in place. With these expansions, we have, of course, cos raised to the power n theta, sin raised to the power n theta, cos n theta, and then sin n theta. For these four expansions that we have, we would notice that it is well and truly enough for us to be able to expand any and every single cosine and sine expansion that we have. In the next video, we will look at some of these examples of these trigonometric expansions and see how well we can use these formulas that we have derived in solving them. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.